Let's take an example from the book. Example 23.7, the electric field due to a charged rod. Page 721. Here we have a rod. This rod has a length L, located at a distance A from the point P. The question is, we have to calculate the electric field created by this rod at the point P. Before we have this rod is uniformly charged, okay? And it has the charge per unit length equal to lambda, okay? Positive charge per unit length, lambda. The total charge is Q. Okay. Let's write the given here clearly. First of all, Q is the total charge. Lambda is equal to the charge per unit length. It's important to know the definition is the charge per unit length. The unit is coulomb per meter. Before lambda can take two values. Lambda can be constant, or lambda cannot be constant. Where lambda is constant, or in which condition we can take lambda has a constant value. Lambda is constant when we have a uniform charge distribution. It's very important. When the charge is uniformly distributed on the object, we can say lambda is constant. It means if we have here an object, this object, the charges are distributed uniformly like this. In this case, lambda is constant. And when these charges are not distributed uniformly like this, we have here a lot of charge. Here you have one, here you have nothing, here you have a lot, here you have one, here you have one. You know that in this case, the charge are not distributed uniformly. In this case, lambda is not constant. Okay, it's very important to know this. Okay, this is the given. Let's draw the given. Here you have the x-axis. On the x, you have the object, the rod. We want to calculate the field at a point P, which is located at a distance A from the rod, and the rod has a length equal to L. Okay. Now, to begin, first of all, you have many steps to follow. First of all, you have to precise. You have to precise the center of position. It means you have to precise X and Y. Okay? Second, okay, first of all, I can take X and Y in the location to facilitate the calculation. Let's take X and Y at P. Here you have X and Y. Y and X. And here the center. To take a small element dq. dq, the form of dq, let's say like this. This one is dq. The length of dq is dl. We can say dl, but when the road is on the x-axis, you have to say dx. If the road is located on the y-axis, you say dy. Okay? It's a small portion on the x-axis. It's dx. 3. Locate the dq. You have to illustrate the location of dq in function of the center. It means in function of the center. Here you have the center. The location is at x. Here we have x. Okay, if you follow these steps, you can solve any question, any problem about the object and the calculation of the electric field at any point from the object. Now let's draw the field created by dq on P. So here you have to put delta E. dq will create at this point a field equal dE. As dq is positive, dE will be in this direction. Okay? I mean, Q will create E. dq, the small portion, will create dE. It's positive, so the charge must be away, directed away. If the charge is negative, so it will be like this. Okay, the equation is, we can we have here dE in general equal dEx plus dEy. You know that dE has only one component in the x-axis. We don't have y component. So equal to 0. So equal dEx plus 0. dx, let's do the projection. The projection will be dEx, which is equal as magnitude dE. We can put it like this. Here we have dEx. So dE equal dEx as magnitude. Okay. But dE equal dEx equal dEx in the negative direction, in the minus I direction. Minus I. It's important to put the direction. Now let's calculate the magnitude of the electric field. We can write here. So we have dE equal minus dEx I. To calculate this one, we do the integral. The integral of delta E equal to E. So E equal minus dEx I. dEx, we said that dEx as magnitude equal dE equal K dQ divided by the distance square between dQ and the location where we want to calculate the field, equal to x square. So we can write here equal minus dx equal K dQ divided by x square in I direction. The most important point is to calculate the limit of the integral. It's very important. The limit of the integral, you know the limit if you move the charge dq from one extremity to the other extremity. At this extremity, dq is located at a distance equal to a. And at this extremity, the charge is located at a distance equal a plus L. So the limit must be between these 2 points, between the position A and the position A plus L. Between A and A plus L. Let's calculate now the integral. You know that it's a linear charge density. So dq must be equal lambda dx. We said in the x direction dl equal dx, in the y direction dl equal dy. So we are in the x direction, we put lambda dx. So here E equal minus K is constant. We put it out. Inside we have here you can put lambda dx. Dx is constant. You put it out of the integral. Okay. We have here K lambda integral dx divided by the distance equal x square between a and L plus a in I direction. To calculate the integral, let's me explain the integral. If we have the integral of a, for example, it's an example, okay? X dx, and here we have 1. The integral equal x 1 plus 1, okay? We put 1 plus 1 divided by the total value equal to 2, okay? And we put the limit between A and B. Let's apply this one to our problem. We have here minus K lambda dx. Okay, let's say here we can put x squared up by changing the power from 2 to minus 2 dx I equal minus K lambda. The integral here, as we said, we put x minus 2 plus 1 divided by the total value minus 2 plus 1 equal minus 1. And the limit will be between A and L plus A. Okay. Equal minus K lambda x minus 2 plus 1 equal x minus 1 equal x minus 1. Minus, we can put here minus between A, L plus A. Don't forget I in I direction. Okay, equal minus K lambda. Also, let me explain. If we have here x between A and B equal, it's an example, okay? Equal B minus A. You put B minus A. So, equal, we come here to our example, equal K lambda. The value, we can put x power minus 1 down by changing minus 1 to 1. Okay, equal minus 1 over x between A and L plus A I direction equal minus K lambda. Okay, first of all, minus 1 divided by L plus A minus 1 divided by A. Okay, I in the direction of I equal minus K lambda minus times minus equal plus and equal 1 over A minus 1 over L plus A. Just we changed the position in the direction of I. So this is the solution of this problem. We calculated the total electric field created by the rod at the point P. At the point P. We see here the value of the electric field at the point P. Let's simplify this equation. Equal K lambda A L plus A. We get here L plus A minus A. I. A minus A equal to 0, so equal minus K equal minus K lambda L divided by A L plus A I. You know that lambda L equal to Q. Q equal lambda L. Okay? So equal minus K Q, because I can ask you to calculate the field in function of Q. I. This is the value of the electric field with in terms of Q. Okay.